Good morning everyone, my name is Kanjana Sela. I'm the first year master's student from Suvarnabhumi University of Technology, Thailand. Today I will present my research about molecular simulation of structural and surface property of the Diblock copolymer freestanding thin film. In this work, I'm interested in studying the new potential property of polymeric material developed from the existing monomer using the concept of creating Diblock copolymer thin film. Outline first, I would like to introduce the Diblock copolymer and phase morphology. Simulation includes cross-grain copolymer molded onto the 2ND lattice, intermolecular and intermolecular interaction, and multi-poly multi-hollow method. Next, result and discussion. Finally, the summary. In this slide, I would like to introduce the general concept of Diblock copolymer. Diblock copolymers are macromolecules composed of two or more chemically distinct homopolymer blocks that are covalently bonded together. Diblock copolymers have been applied widely at the temperature for their amazing ability to be self-assembled into the variety of the other microstructures in the preparation of nanomaterials, such as organic photoelectrochemical nanomaterial, biological medicine material, and photonic crystal. Due to the extensive application of Diblock copolymer, it is important to study the macrophase separation of Diblock copolymer. Material made of the Diblock copolymer are used mostly in tribal form, and more recently are finding increasing application as thin film. For both systems, the Diblock copolymer can have many different morphologies depending on comonomer composition. In this work, we are interested for the case of Diblock copolymer in thin film geometry. We want to know how the structure, morphology, dynamic, and surface property will be changed as a function of comonomer bit interaction. Here's the overview of our simulation method for the Diblock copolymer. First, the IH model of a single chain of polyethylene was used to describe the interchain interaction. To simulate the both systems, we introduce the Vao-Soongnern non-bonding interaction. The coach-gain polymer chain will map onto the second nearest diamond or 2ND lattice. To model the copolymer, we use the different interaction parameters of non-bond based on the Vao-Soongnern potential, which vary as well as the 120 and 250 at the state of comonomer interaction. Next, we create the thin film from the bulk structure by increasing the periodic bulk size in the one dimension so that its mirror image cannot interact with the parent chain. And then we use the multi-hollow simulation with the multiple criteria to move the polymer for the incubation and trajectory for data analysis. In general, fully atomic model of polymer was the carbon backbone has one exchange geometry suitable for map onto the diamond lattice. We then group two carbon backbone into the one coarse-grain bit. A new structure is from called 2ND lattice. For the movement of bit on the lattice, they show a chain of chain conformation, where each the position on lattice can be represented by nine conformer such as tan, gosh pat, minus, and gosh minus. In this slide, I would like to introduce the intrachain interaction. The IH model is used to describe short-length interaction, which depend on the polymer conformation. The IH model has three states of each bond edge: tan, gosh pat, and gosh minus, which include first order and second order interaction. The interchain interactions are obtained from the described from the Vao-Soongnern potential on 2ND lattice. The method is used to distill parameters similar to statistical thermodynamic treatment of real gas using the second variable coefficient, but in the discrete space. Only the first feature of the interaction parameter were used to speed up the simulation. To model the copolymer chain, we employ the different volume of value parameter or the epsilon. The multi-hollow simulation is based on multiple criteria which was applied to determine whether the move was made or not. Following this scheme, where the T is energy difference between the new and old conformation, which includes both short and long-range interaction. R is universal gas constant and T is absolute temperature. If delta E greater than or equals 0, the move is accepted. Otherwise, a random number is generated uniformly from 0 to 1 used to determine whether the move is successful or not, by comparison with the Boltzmann weighting factor. Next is result and discussion. This slide shows the monomer distribution in the T direction for the T system. The relaxation of initial structure is needed to validate the equilibrium and can be monitored using the orientation autocorrelation function, which is defined using the end-to-end vector of the polymer chain. The complete relaxation of both copolymer structure can be achieved within 70 million multi-hollow steps added by the decay of end-to-end vector to less than 0.37. And then we calculate the autocorrelation function of each piece. The results show that our system will equilibration, and the decay rate of end-to-end decorrelation function is lower for stronger bit attraction. The mean square displacement of the center of mass diffusion for the molecule and each bit show a similar trend to the orientation autocorrelation function, and equilibrium can be judged by the MHD should accept to RG. To the comparison dynamic of the monomer level, we use the mean square displacement of the monomer bit. For a homopolymer chain, the curve is symmetry for the Diblock copolymer. For the Diblock copolymer, we observe the asymmetric curve which increase bit attraction. Bit mobility becomes slower and curve become asymmetric. The density profile for the Diblock copolymer are presented. We observe the copolymer separation in the Diblock copolymer thin film. As the interaction becomes stronger, the film density increases, stronger copolymer separation and sharper surface. The Diblock copolymer has clear copolymer separation because the copolymer strong has a covalent bond between the two different bit types. Next is the density profile of two different bits. It seems that the system which more attractive have higher bond density, and the Diblock copolymer exhibit copolymer separation. This slide presents the mean square radius of gyration of the molecule as a function of the displacement of center of mass for the film. We separate the change in the radius of gyration into the two components according to the direction of xy span and z direction both sides. The xy components seem to be similar size, and the z component becomes smaller as the chain approaches the surface from the both sides. When the copolymer attraction increases, the chain will become smaller. The chain orientation at the molecular level can be investigated using the orientation of the largest and smallest eigenvector of the own chain. The orientation of largest and smallest principal moments to film surface. Both axes are randomly oriented in the bound region, whereas there is strong tendency for the first principal axis to the orient parallel to the surface and the third axis perpendicular to the surface. The strong repulsion shows random orientation more than attraction, and the increasing interaction seems to cause a larger anisotropic arrangement at the molecular scale. Phrenicity. The interchain energy are decreased from the more repulsion copolymer and usually drop at the surface region. The interchain energy are increased for the more repulsion copolymer and increase exponentially at the surface region. It may be explained that chain conformation can adopt a more tight state which has lower interchain IH energy, and the interchain interaction become higher due to the better molecular packing, or the copolymer bit can come close to the repulsive portion of the Reynolds potential that is less than 5 angstrom. The summary. The molecular simulation method to study thin film composition of the amorphous polyethylene Diblock copolymer were developed and tested. The nanofilm can reach the bound density in the interior. For the structure, the film was larger, copolymer attraction have higher density and sharper surface. Polymer chain in the film become destroyed in sharp and exhibit an anisotropic arrangement, and the mobility are decreased for the stronger attraction between different monomers for the both rotational and translational mode, especially in the region near the free surface. Thank you for your attention.